Start recording. I now share my screen back. Okay. Okay, today we'll be discussing material from the 3 chapters of the book, chapter 1, chapter 3, and chapter 5. And we actually start with chapter 3 with a basic introduction to sets and operation on sets. And chapter 5 contains material on functions, Cartesian product of cells, injections, bijections, surjections, bijections, and so on. And then finally, by the end of the lecture, we'll start counting things, because that's what combinatorics is about. So combinatorics is the art of counting different configurations, collections of objects, and so on and so on. It's very useful topic in mathematics, used in many different branches. Some people consider it's a very trivial topic, but maybe since the 60s, the 70s, a new branch of combinatorics has been developed called algebraic combinatorics, and it's much more advanced than elementary combinatorics used to be. But in any case, I think it's a nice topic. So in KTH, there is a fairly big group of combinatorialists working on this full time. I'm not a professional combinatorialist myself, but I've definitely counted combinatorics in many research topics. Okay, so let's start. Okay, so we'll start with, let's see, sets and operations on sets. And this is chapter 3, maybe 3.1, 3.2, section 3.1, 3.2 from the book. Okay, well, it's to define what a set is formally is not completely trivial, but we basically rely on intuition, and no actual formal definitions will be necessary. In this course, we'll be only using finite sets where no substantial theoretical difficulty can occur, which is nice. In general, set theory was developed in the end of the 19th century by Georg Cantor, who was a German mathematician of Jewish origin. And the theory which he developed, he ended up in the mental hospital for different reasons. In particular, he thought that God Almighty sent him this knowledge to distribute among people, and so on and so on. So if anybody is interested in history, mathematics, I can recommend some nice reading about his personal life and so on. But the naive set theory which he developed very soon ran into substantial theoretical troubles, which luckily for us does not appear in the case of finite sets. And then there was a whole long story of development of mathematical logic in the early 20th century, whose major reason originally was to overcome the difficulties of naive Georg Cantor's set theory paradoxes, which appeared immediately. But then eventually it became a very useful subject in connection with computers. But this happened later. Let's see. Okay. Anyway, so we'll rely on a set as a collection of some kind of objects. Can be collection of finitely many objects or infinite collections of objects. And yeah, members of these collections will be called elements of the set. So in particular, one interesting example of the set is an empty set. Example. So empty set is quite important abstract notion, and it's denoted by this small zero with a line crossing it. So other examples would be, so sets are usually denoted by these figure brackets, which contains a list of elements of the set. So this is the set containing of n first natural numbers, 1, 2, 3, and so on up to n. So for example, n, this probably you know this notation, this is the set of all natural numbers. Yes. Z, notation for all integers. Then Q is the notation for all rational numbers. And these N, Z, and Q are all so-called countable sets. Maybe you heard about that. If not, I'll recall it very briefly. And then if we look at R, which is the set of all real numbers, this is the first example of an infinite set, which is not countable. Okay, so the basic notions we will be talking about. Okay, so okay, the important definition is as follows. Two sets are said to have the same cardinality. Cardinality is a generalization of a notion of the number of elements. For if the set, okay, let me finish the definition. If there is a one-to-one correspondence between the elements. So if we have two sets containing finitely many elements, so then we can make a one-to-one correspondence between a set and numbers from 1 to certain number, m, for example, where m would be the number of elements. And then two finite sets have the same cardinality, of course, if they have the same number of elements. But in general, if sets are infinite, for example, as the set of natural numbers or the set of real numbers, we cannot talk about the number of elements because it doesn't exist. It's infinite. But infinite sets can still have different cardinalities, different number of elements, so to say. And the first fact which you have probably learned in your elementary calculus course is that the set of real numbers has more elements than the set of positive integers. On the other hand, the set of positive integers and the set of all integers and the set of rational numbers, they have the same cardinality because all integers can be enumerated by positive integers, and even all rational numbers can be enumerated by positive integers. And for example, the set of all points in the plane where both coordinates x and y are integer or rational numbers still have the same cardinality as just the set of positive integers, and these sets are called countable. So countable sets are the simplest type of infinite sets. They contain as many elements as their natural numbers. But then there is a whole the whole, how should I say, the whole sequence of sets which have more and more and more elements in terms of cardinality. For example, R has more elements than positive integers, and the claim that R is the minimal non-countable set turned out to be an axiom. It's independent of many other things which we know about arithmetic, and this was the so-called continuum conjecture, and so on and so on. But then there are sets which have more elements than the set of real numbers, and so on and so on and so on. There is kind of an infinite sequence of sets having more and more and more elements in terms of cardinality. Okay, but that's not our major topic here. We'll be mainly concentrating on finite sets, so we'll not be running in these complicated issues. Okay, so let me recall some basic operations, basic notions of the set theory. So the first definition, maybe, so this would be definition 1. Definition 2 would be given two sets A and B, we say that A is a subset of B. Well, if each element A in A belongs to B. So we'll be using small letters for elements and capital letters for subsets themselves. So small a would be an element of the capital A. Capital A is a set and small a is its element. Okay, so some trivial examples. An empty set, by definition, belongs to any set. That's kind of a matter of agreement. For example, we have natural numbers are contained in all integers, are contained in all rational numbers, are contained in all real numbers, are contained in all complex numbers. So this is a set of inclusions. My definition 1, okay, this is the cardinality. Okay, so when do we say that two sets are equal? Two sets A and B are equal if both of them are subsets of the other. If A is a subset of B plus B is a subset of A. So that means, in other words, that they contain the same, exactly the same collection of individual elements. Okay. Yeah. Let's see what do we do further. Let's define basic operations. So I'm sure that you know them as well, but let me still recall this. And for the basic operations, we have to assume that all sets we'll be working is are contained in one set which lies behind, which is called the universe. So assumption for the definition, all our sets are contained in some universal set, say U. I think that's also used in the book. Otherwise, we can run into some difficulties. But this U will never appear in our specific consideration, but we have to keep in mind that all sets we work with are contained in some global, universal something. So we have to think about that. Let's see. So given A and B in this universal thing, we define their union. This is the notation. So, well, as which is by definition the set of X in this universal set such that either X belongs to A or X belongs to B. Now the intersection, again, you surely know, is the set of all X in this universal thing such that X belongs to A and X belongs to B. Now, we can also define, so this is our first operation, this is our second operation, this is our third operation, the complement, which is the set of all X in U, such that X does not belong to A. What else? Maybe this notation you have seen before, B minus A minus B, I'm sorry. This is the set of all X in our universe such that X belongs to A and X does not belong to B. So I hope that this inclusion sign, yeah, you have met before, yes. Okay. Yeah. So in connection with this, we can say that I think it's definition 4, a disjoint union of A and B is A union with B under the assumption that A intersected with B is an empty set. Okay, what is a good example for that? Example, N, the set of natural numbers, is a disjoint union of odd numbers, union even numbers. Any positive integer is either odd or even, but also the intersection of the set of all and even numbers is empty. So this is a disjoint union. And we can have more than two things forming a disjoint union. For example, yeah, let me, well, a lot of things like a disjoint union. Okay, so say odd numbers consist of numbers which are, say, which have which have rest, which have the remainder either 1 if divisible by 5, or 3 if divisible by 5, or 0 if divisible by 5, and similar things. Okay, good. Let's see, some basic rules of union. Let me see, I have this noted somewhere. Just 1 second. Yeah, here. Some laws of set theory. Some basic laws of set theory. Okay, the first one is the double complement is the set itself. Yeah. If we take the complement of A in our universal set, so we'll get all elements which are in our universe which are not in A. And if we take the complement of the complement, we'll get A back. Fairly straightforward, rather simple thing. Now, if we take the union and then take the complement to the union is the intersection of the complements. This is also, so all laws I'm stating here are rather trivial, but it's a nice exercise to think them through. If we take the intersection of two sets and take the complement, what happens then? Well, I'm claiming this would be the union of individual complements. Okay, maybe we should prove some of them. Now we have this commutativity of the union and the product, which is fairly obvious. And similarly for the intersection, A intersected with B is the same as B intersected with A. Then we have, for example, this is a nice distributive law. If we take the intersection of sets B and C and take the union with A, so how can we express it differently? Well, the thing is that we can take two unions, A with B and A with C, and then intersect those. And similarly, we have with the operations intersection and union changing places, we'll have this, we have this kind of relation. Okay, maybe you are already familiar with all that. Let me just prove I don't know this thing, just as a small exercise. So we're saying that if we have two things, A and B, taking the intersection, and this is our universal set U, and I am saying that now we're interested in the complement to this intersection. Yeah, the complement, I don't quite know how to, I'll put small dots. So this would be the complement to the intersection. And I'm saying that this is the same as, I should take the complement to A. So here my A and B again. So this is A and this is B. So I should take the complement to A, maybe denoted by these small stars everywhere. Oops, no, this was wrong. I'm sorry. I have to remove that. Yes. And now I have to take the complement to, where are we now? the complement to B, so denoted with such small round dots, and take the union. So everything which I draw with small crosses, together with those things which are with small dots, the union is the same as the complement to the intersection of A and B. And the formal proof, this is an illustration of the proof, and the formal proof would be as follows. So what is the complement to the intersection? So we're taking the intersection and taking the complement. What is that? So these are all x in our universe, such that what happens? They are not in the intersection. So either, okay, how should we express that? Okay, they are not in the intersection. Not in the intersection. Either x does not belong to A and x does not belong to B. Or x does belong to A and does not belong to B. Or finally, the first version is that x does not belong to A, but x belongs to B. So what can we conclude from these three options? That either x lies in the complement to A, or x lies in the complement to B. And that's exactly what the right-hand side of this thing describes. So we're not lying in both A and B simultaneously. Okay, but these are all very simple things, and hopefully you have seen all of that. So the next notion, which is important, is a product of two sets, Cartesian product. Cartesian product of A and B. Notation is A cross B. And here the order might be important, but it's first A and then B. Okay. And what is that? So this is by definition is the set of all ordered pairs small a and small b, where small a belongs to A and small b belongs to B. So this is quite important operation on the sets. We'll use it quite often. This will be also connected to the notion of relation. Yeah, so what would be a good example? What would be a good example? For example, R2, the plane is a Cartesian product of R cross R. So the plane, we use this all the time. So each point in the plane is a couple of coordinates, the first coordinate and the second coordinate. Yes. So this is in this sense, yeah. it's a Cartesian product of two copies of the real line. So maybe some other, okay, what could be? So car numbers, car plates, yes, registration plates for the cars could be in Sweden, at least used to be. What did we have earlier? 3 letters plus four numbers. It's a Cartesian product of 3 objects alphabet. So let's assume that there are no exceptions. Times alphabet again, times alphabet 3 times because we have 3 letters, times digits, times digits, times digits, times digits 4 times. So it would not be pairs, but it would be 7 tuples consisting of a letter, a letter, a letter, and a digit, and digit, and digit, and digit. Okay, yeah, we'll definitely meet more examples of Cartesian products later on, of course. So let me talk a little bit about relations and functions on sets. And now we are moving to, so this would be from chapter 5, sections 5.1, 5.2 in the book. So often we have relations between elements of the set or between elements of 2 different sets. Well, the trivial example would be, I don't know, if we're taking males and females, then the relations are being engaged or have something like this, married. And so how do we think about relations? And functions would be a special type of relations. In general, a relation in mathematics is, maybe it will take a little while to get used to that, but it turns out to be a very useful notion. So next definition, and I lost track of which number would be, I think something like 6, would be given 2 subsets, 2 sets A and B, can be arbitrary sets, a relation between A and B is an arbitrary, in general, an arbitrary subset of Cartesian product A times B. Okay, so looks a little bit abstract, but let us make some concrete examples so it would not be as abstract anymore. For example, if we're working with real numbers, so we know what does it mean that one number is bigger than the other number. So what about x smaller equal than y, where x and y are real numbers? Okay, so what is that? Well, let's look at R2, which is the Cartesian product of x and y. two copies of real numbers. And I'm saying that a relation, in this case, the relation of one number being small or equal than the other number is some subset of the Cartesian product. And in this case, the Cartesian product is just the usual plane. Okay, so we can draw what is the domain in the plane where x is smaller or equal than y. So if we draw the diagonal x equal than y, so then we have to take the half plane which is to the left of this line. In this domain, in this half plane, x would be small or equal than y. So what is the relation? The relations could be really very different nature. What about x equal than y, for example, again? Well, that's just the diagonal, yes, of course. So here x equals y. What about something like x squared plus y squared small or equal than 1? That's again a relation, yes? So the relation says that the sum of squares of two numbers is at most 1. Well, we know what this is. This is the domain given by the unit disk. But let's make something more closer. Yeah. Something of more usual nature. What about being a sibling? Yeah. So if we look at the space again of all people, living people, I don't know, even all people, and again times all people. And for each person here, for example, here we'll mark along the other axis who in the whole world are his or her brothers or sisters. So this will be again be a subset in the Cartesian product of the set of all people times itself. So really being a general relation is a quite general notion. And it can be always expressed as a subset, some subset of the product. Of, yeah, if we're talking about two different sets, it would be the product of A and B. If we're talking about some subset in some relation among elements in the given subset, like among people, I don't know. We can talk about something which species of animals are relatives to each other, which originate from the same root, and so on, which have DNA sequences different by at most 20%. All this can be expressed mathematically as some subsets of Cartesian products. Okay. Now, just to do some exercise, let me ask you the following question. So given two finite sets with n and m elements, finite sets A and B, with n and m elements respectively, how many relations among A and B exist in general? So let me wait for some 10 seconds for you to try to think it, and then I'll try to explain what the answer is. So we're talking about, first of all, so I have said that the general relation is any possible subset in the product set. So solution. So the first step would be step one. Step one, how many elements A times B contain? Okay, so if A and B are finite sets, then the Cartesian product, as I mentioned, is the set of pairs. We have some element A from capital A in the first place, and there are totally n possible choices. And we have a B from the capital B on the second place, and we have m possible choices. So the answer is that the cardinality, the number of elements in AB is obviously n times m. Okay, so if we have, for example, a choice of 3 pairs of pants and 2 different shirts, then we have totally a choice of 3 times 2, 6 combinations. Yeah? We can have 1 of 3 possible pants, and we can have 1 of 2 possible shirts. So that's a generalization of the statement. Now, step 2, maybe this is a little bit less trivial. How many subsets, possible subsets A times B contains? Well, let us answer this step 2 in a little bit more general setup. If we have a finite set with capital K elements, how many possible subsets do we have? Say, what about subsets in C where C contains, say, K elements? And if we answer that, then we'll answer in this special case what we need to know about A cross B. Okay, the answer would be here is 2 power K. So there exist 2 power K subsets in C, which contains K elements. Why is that? Well, so we have K elements here, yes? So here is the proof why the answer should be 2 power K. So we have 1, 2, 3, K elements. And for each element, we choose either a 0 or 1, or either plus or minus if you want, I don't know. Plus if we take it, minus if we don't take it. So to choose an arbitrary subset means to choose a collection of signs, either plus or minus, for each position of K. For each element in our set, we choose either a plus or a minus. Well, so how many combinations of pluses and minuses we have? Well, we have K positions, and at each position we should choose either plus or minus. So we have totally 2 power K collections, possible collections of plus minuses on k positions. That's why for a subset with k elements, there exists 2 power k. For a set with k elements, there exist 2 power k possible subsets inside here. So going back to our situation, we have that A times B, it contains n times m elements. So our answer is 2 power n times m. N times m is how many elements A times B contains, and then using this argument which I just gave you, we conclude that there are 2 power n m possible relations between the set of n and the set of m elements. Okay, so I suggest that we make maybe a short break now, 5 minutes, and then I'll resume and I'll try to explain some basic principles of counting. Okay, short break now.